Okay, so you've already heard me preview this, but why is linearization nice at all? It's you can start with z equals f of x comma y being anything. It could be a very chaotic function, and then the linearization is very nice, right? The linearization, all the parts highlighted in yellow will eventually just be numbers. They'll just be some constants, right? And these are just five different, possibly different anyway, constants. And so the linearization is just of the format number plus number times x minus number plus number times y minus number. That's a really nice function, right? So your z of f of x comma y, z equals f of x comma y could be a very, very, very complicated thing. But the linearization, it's going to look like this. It's going to be L of x comma y equals 6 plus 7 times quantity x minus 4 plus 8 times quantity y minus 3. I mean, obviously this one's really nice because all the numbers here are whole numbers. Maybe you have some decimal otherwise, but the point is that's just really nice, right? The point is the type of function you're looking at here, it's about as nice as you could expect a function to be for a function with two input variables without just being a constant function where the output is just literally always the same number. There's a brief connection to linear algebra that's worth mentioning here. This function that you see here, I know it's called a linearization, but in linear algebra, this is not a linear transformation. The issue is that um, this graph does not go through the origin, which is a thing that you would need in linear algebra technically to have a linear transformation. Now, if we just temporarily moved uh, the axes so that 4 comma 3 comma 6 were treated just temporarily as the origin, then you would have a linear transformation. So look, the arithmetic of computations is so nice that even in very, very high dimension, I mean, this is just a three-dimensional example, but you could do this in higher dimension. An entire class called linear algebra is devoted to studying linear transformations. This idea of, okay, what we have is not technically linear transformation, but just move the axes temporarily, do some linear algebra-like work, and then remove the axes back to where they belong. Okay, so let's find the linearization of f of x comma y comma z at x squared minus xy plus 3 sine of z at the point 2, 1, 0. So this is a function of three variables, and we did not present what linearization looks like, but this is it, right? Like, I hope it's not too surprising that you take the actual double w value, so f of a comma b comma c, and then you've got three terms that look a lot like the kind of things that come from a point slope form. Right, so we compute these three individual partial derivatives first, evaluate all of these at 2, 1, 0. All of these are hand calculations, right? So we've got sort of slopes in various directions of 3, -2, and 3. And then we need the actual w value, the actual output of the original function. So that's an algebra and trig step. We get the value 2. This is completely done by hand as well. And then when we place all these things together, this 2 gets copied here. So 2 plus, and then this first slope-like thing, this derivative, partial derivative value, 3 times quantity, x minus 2 from the original problem, plus -2, so minus 2 times quantity y minus, and then the 1 that was given originally in the question, plus 3, that's this final slope-like thingy, the partial derivative value 3 times quantity z minus, and 0 was given in the problem. Look at how nice the linearization is, even though the function, and this function wasn't bad, but I hope you get what I mean. The linearization just always has this very predictable format, and the follow-up is that the point x comma y comma z equals 2.1 comma 1.3 comma 0.2 is very close to 2, 1, 0, right? I just picked a little bit of a decimal to attach to the 2, 1, and the 0. And so if we needed f of 2.1 comma 1.3 comma 0.2, but we're willing to trade a little accuracy just to do something a little nice, a little simpler, then we could find the linearization at 2.1 comma 1.3 comma 0.2. So let's do that, right? Now, this is really a hand-done calculation, right? 2 plus 3 times quantity 2.1 minus 2, minus 2 times quantity 1.3 minus 1, plus 3 times quantity 0.2 minus 0. You can let me just point out how you do this by hand. There's 2 is copied. Look, 2.1 minus 2 is 0.1. So 0.1 times 3, that's 0.3. And then here in parentheses, 1.3 minus 1 is 0.3, and then, well, 2 times that, so 0.6, and copy the minus sign. And then lastly here, 0.2 minus 0, there's no work to do. 0.2 times 3 is 0.6. And if you look here, negative 0.6 plus 0.6, that's gone, right? So we have 2 plus 0.3, literally 2.3 completely done by hand. There's no need for a calculator in any of the work so far shown on the screen. However, think about if you wanted the actual value, f of 2.1 comma 1.3 comma 0.2. So that's 2.1 quantity squared. I can do that by hand, although it's a little annoying. Minus 2.1 times 1.3. I could certainly do that by hand, though it's a little bit of work, but not too bad. The last part's really the issue. Plus 3 times sine of 0.2. I don't do this by hand. What am I supposed to do? I mean, how am I supposed to do sine of 0.2 radians by hand? So the rest of this stuff is, I mean, kind of all of the terms here are, well, they're tedious terms in the first two, and then the third term is just, yeah, what would you do by hand anyway, right? So I hope you see, look, just even by hand, I mean, even if you wouldn't do these things by hand, the fact that you can by hand work with an approximate value just tells you how nice linearization really truly is.